So first thing we're going to talk about kind of is more broadly intelligent robot architectures, because you kind of go from little robots that are like line followers that don't have a lot of intelligence beyond sort of insect-like, just follow the line intelligence, and you go to the other extreme, which is the goal, the highly autonomous, self-aware kind of robots on the other extreme, right? And so where do you fit into those, and what are the common pieces that you put on as you become more and more advanced with your robot? So we start at the bottom, I call it the driver layer at the bottom, and this is what we're all very familiar with here. Sensor interface, the actuators, inter-robot communications, the wireless networking, or the communications between the pieces, are a very fundamental hardware level. Very specific. You're programming to that specific sensor, right? It's not just a laser rangefinder, but it's this specific laser rangefinder with specific protocols and communications that it has to have, or whatever, for your sensors. Go up a layer on top of that. Now, as we go higher in the stack, we're going to go from implementation at the very bottom to more policy. And architecturally, you want to separate them. So you want to push your policies up and your implementations down. So our next layer up is a little more abstract. Steering, the sensors, bringing all the sensor information together in one spot, your image processing, and your kinematics, which is the math of your joints and components, your articulation pieces of how the robot moves. A little more abstract than the hardware interface, but still pretty much based on what your robot is built to be. Right? If you have a 3-element arm with an elbow on it, your kinematics are going to be for that robot, and it's going to be hard to transport that to a different robot unless it has a similar 3-element arm. Go for another layer. Now we're at the algorithm layer, and this is where it becomes less specific to the robot you're doing. So your path planning, how do you get from A to B? How do you avoid obstacles that show up in between? An unplanned, this can be a person or an object moves across your path. How do you avoid that? Or in the case of a SLAM kind of a situation where you're building the map as you go, if you encounter an obstacle you previously didn't know about, how do you adjust your path to avoid that? The mapping and localization, again, like the SLAM we talked about a year or so ago. And then your task definition is what is it you're trying to accomplish? Go up to the higher level now, this is your goal layer. I think this is a very interesting piece. And when I had to think a lot about what are the categories for this, and often where I kind of stop at a robot, when I build a robot, it's like, well, what do I really want to do? So you can have a robot whose goal is to explore. Simply move into an area, map it out, move around, be sure you have all the coverage of it. Courier delivery robots. I'm going to have a robot that brings me something or takes something somewhere else. That's its goal. Move and improve, which is building, right? Robots that would go autonomously to Mars and pre-build a habitat there would be, move to a location, build stuff. Improve is not improve itself in this case, but improve the environment around it. And then the last one I came up to was a self-improve robot. So go and learn. Different algorithms are unsupervised learning, so the robot gets better at tasking practices. So that's sort of all the goals. And above the line, you often have software that the user interacts with the human. So you want to see what the robot sees, so you're seeing your video, your teleoperations. You want to take over the robot and run it by hand. Your health displays. You want to understand, is a motor getting too hot? You have telemetry coming back from the robot, sensor and telemetry display. Where is it? What's it doing? Is it following your commands? Or is the battery low? Or the motor's hot? Those kind of things are important for the user to understand, the user to be part of. So what we're going to talk about today, out of all these, is this one little piece. And of this, we're going to talk about one little piece of this one little piece. About how do you decide, given one of your goals, how do you make the robot get from point A to point B successfully? So that changes. So this says 3D planning. Really, it's 2D and 3D all fall into the same piece. I was going to talk about two different algorithms today, but I really decided let's cut it back to one, spend more time with it, and then at some point we can talk about the other type. But there are 5 main categories of path planning. The sampling-based, the node-based, which we're going to talk about node-based today. There's mathematical model-based, which is a function where you just tell the robot, follow this y equals f of x curve, and it does that somewhat blindly. Bio-inspired algorithms, neural nets, genetic algorithms fall into that category for path planning. And then multi-fusion based, which is taking different pieces of these things together and combining them. We're going to talk really today about a node-based algorithm. And in node-based, this further categorizes up. There's a lot of research and a lot of different algorithms that we can use here. Dijkstra's algorithm and versions of that is one of the original path planning algorithms. It's an exhaustive search of the map to try to find the best path between 2 points. Then there's A star, LPA star, theta star, and lazy theta star. These are all optimizations of Dijkstra's algorithm. So what they do is they start out doing an exhaustive search of the entire map for the best path, but they'll recognize suboptimal paths. When you found a better path, they'll stop looking at the poor ones. And so it's an optimization. And then D star light, and so on. Again, there are variations on a theme, a little bit different approach to it. You would use the different of these algorithms. You kind of pick based on the environment you're in and how much you know about it, how many obstacles there are, and how fast the algorithm has to compute the path. In the case where you've got an environment where obstacles can suddenly appear because you're building the map dynamically, or people or objects going to walk in front of your path, or it could change, you're going to rebuild this path continuously. Okay, you're going to build a path, start to move, and then as you get new sensor input, you got to rebuild the path when new information comes in. And so speed for these things can be very important. Sampling-based algorithms are interesting. We're not going to talk about them today. I was going to, but I just, in interest of time, we could do that at a later point. So we're going to talk about the A star algorithm, which is certainly the most common. There's a ton of code out on the internet in every language, every environment you can imagine. ROS, I'm sure, has a GOB of A star. There's Java applications, C++, C, assembly level. All of these things are out there. It's a very common and a very effective algorithm. And the A star algorithm finds an optimal path through a directed acyclic graph. So if you remember back to your math, your geometry days, the graph is just a connection of nodes with link paths between the nodes. And a directed acyclic graph means you can go from 1 to 2, but not from 2 to 1. There's a direction in your travel that you specify. And it's acyclic means there aren't cycles. You can't get into infinite loops. And so that's the kind of a model that an A star algorithm can solve. It doesn't have to be a dense grid. It could be nodes between cities, and you want to find the traveling salesman problem is essentially a form of A star algorithm. So what we're going to build is slow. Okay. We're all familiar with the idea of a map, right? So there's a data structure in memory that represents the room that your robot is in. You're going to for A star, we're going to represent that as a directed acyclic graph.
Notice that map could be dynamic. It could be, this is the map. I mean, theoretically, you want it to be there all along. But that could be dynamic where you're going, I moved one square, and now I need a new map. The same program can handle that.
Right, it can. Yeah. But again, you got to if something new shows up in the map, you got to recalculate your path to be sure it doesn't affect what you're doing. So you're gonna build a grid. Let's say we grid out this room. This room is our area where our robot's gonna operate. We would build a map. It's what, probably 35 by 20, roughly, I'm guessing. So we would build a map that has a grid of some square size, some fixed size, in the tile size. So in this case, I've shown a room that has 1 foot by 1 foot squares. You could make them 10 foot by 10 foot. You could make them 6 inches by 6 inches. The robot, the path that it's going to build, is going to go from the center of the grid to the center of each square to the center of the next square. So that's the path it's going to build.
That means the size of the grid actually is related more to the clearance of your robot than to the size of the room.
And the precision by which you want to build the map. So if you're building a 1 foot by 1 foot grid, you have 6 inches plus or minus of accuracy based on the path. If your robot's 3 feet wide, having a 1 foot grid probably is a little overkill, because a 3 foot wide robot's gonna take up more of that space. If you've got a 2 foot door that you want to get through, having a 3 foot cell size isn't going to let you get through the door well, because you'll be in the middle of the cell, which is probably not the middle of the door. So you need to you're making these kind of trade-offs, these assessments as you're building this grid out. Most important piece here is the memory available. So you have to store this in memory, and if you've got, like most robots, a limited amount of memory, you got to be careful how big you let this grow. If you're doing something like a drone, which this algorithm works just fine in 3 dimensions, you have a 3-dimensional box you got to build. And so the memory to hold this can get really big really fast. But let's assume we've got as much memory as we want to play with here. So I build up this grid. 1 foot, we're going to use 1 foot squares or 1 unit squares. I'm going to specify a start location, which is the red square, a goal location, which is the blue square, and then no-go areas. No-go areas are off the edge of the map, and I put an obstacle, the table, in the middle of the room that's blocking your path.
And the robot knows where all this is, including where it is itself.
By various means, right? By whatever you want to do. Now that could be various versions of exact. I could build this map and take a tape measure and measure where the table starts and where it ends and how big the room is, and then construct that map in memory based on those dimensions. Or I could.
Okay, in that case, it would be determining where it was based on those map measurements as a reference.
On where I put it, yeah. I'm going to put the robot in that corner, and I'm going to put this table right here.
Mm-hmm.
I'm going to reflect that as data in my program.
Okay.
That's one way to do it.
At this point, you're already assuming that the robot knows the map and it knows where it is.
Yes, that's
The path planning isn't
But
doing that.
you could make this into an iteration thing where when it comes up with new information, it would go and start over, make that map, the new map, and then go with that information. And it would be optimizing as it goes.
So yeah.
Use this. Yeah, this is a higher level thinking thing rather than just did my radar work.
Right, and so, but think of it, you could go either extreme. Right? I can build this map out explicitly, measure out coordinates, put them exactly where they belong in this map, and represent this room in that data structure inside my computer. Or I could have it be a completely blank map. I could just put the robot down, have it start scanning, and use SLAM or use some other technique to build where its starting location is, and identify the obstacle that it sees from its starting location.
Yeah.
Okay, I could do either one,
Mm-hmm.
right? If I do the latter and I have it just set it down and let it figure out where it's at and place itself in the map, then as more information, as it drives down this side of the table and it discovers more information, I have to rebuild my map or update my map, just like we did in SLAM, right? Updating those positions.
Mm-hmm.
But every time I update a position on the map, I have to go back in and rerun the algorithm to recompute the path from where I'm at right now to my goal Because I might come up here and realize there's something blocking me I didn't see back there. Right, so I might come up and see it, oh, I can't get that way, and then turn around and have to go back the other way to get to the goal.
Notice because of what you identify there, you really only, you've got whatever your starting location is. So if it's just wherever you are now, start shooting out your rangefinders. You do have to have a no-go area, which could be your, like, let's say you're using a laser rangefinder. That would be there, and you have to have a second sensor somehow that can tell it where the goal is, or what the goal
Well,
is.
that's where the human interaction comes in.
Right.
Back to that
could be the
list.
sensor, could be an input.
Back to this, right? What's my goal? Am I just exploring?
Mhm.
Okay, in which case I'm going to move around and map everything. My destination point is going to be somewhere I haven't mapped. So I'm going to pick, okay, I don't see over here. I'm going to go try to find all the walls as my goal. That's what I'm doing, explore. If I'm doing courier delivery and I want to take something and set it on that on that chair over there, I have to know where the chair is, right? Or I have to explore until I find the chair and then switch to the courier delivery piece. Okay, so that's where but that's happening way up above. That's happening at a different layer in the architecture. That goal is being set. And that goal might change as you interpret new things in the environment.
So there's the dynamic updating. Seems like it would be a big computational task, which makes me wonder how humans are able to do it so effectively.
Our sensors are excellent.
Yeah.
We have sensors that are able to do that without even, right, our vision, our depth perception, our proprioception is so extreme compared to what a robot can do, right? A robot is blind and deaf and has maybe one finger they can sometimes stick out, or a stick they can go out and tap stuff with, right? So that's one of the things we take for granted is our ability to sense the environment around us.
Or just think of a little baby and go, yeah, well, a newborn baby,
Yeah.
he doesn't really navigate very well.
Right.
He's got to learn all these sensors.
Yep. All right, so that's the idea of how this map goes. You have a lot of options here, depending upon what your real setup is. You know very deterministically what the room and the environment looks like, and I can pre-build that into it, or do I have to do discovery? It doesn't change a lot about the way the algorithm runs. It changes how often that higher level of control reruns the algorithm, but the algorithm is essentially the same thing. Okay. The other thing we need to do is assign for each square. Let's go back and talk about this map, right? So remember we had this acyclic graph thing. So what is that? So in this world, this acyclic graph, each square is a node in that graph, and there is a connection, a line between that node and all of its neighbors, unless it's an obstacle, right? So that node has child nodes, or next node down the list, right, of the surrounding neighbor nodes. This node has neighbors here, but the obstacle nodes don't exist. Okay, they're not part of the graph. So then I assign a square of a cost to each of those links between the nodes. So if the links are vertical or horizontal, I'm just going to say the cost of that move is 1. If it's diagonal, because it's a little farther, right, square root of 1 over the square root of 2 to get to there, right, it's 1.4 is the cost of a diagonal move. If I had rough terrain, if I knew this carpet was rough over here and would slow the robot down, and I knew that side was smooth, was tile, I could assign those to be different values. I could say it's 1.5 here and 2 for the diagonal moves on this side, and leave that as 1 and 1.4 to say you're going to be slower. It's harder to go this way. You can make it, but you might be able to go farther, quicker around the other way, and get there first instead of going this way through the slower route. That might be a shorter physical path.
So it's like a cost function, you're trying to minimize the cost.
It's exactly what you're going to be doing, right? You're going to end up, we're going to talk about that in the next slide, but you're going to end up minimizing the cost it takes to get there. The other thing we talked about a couple months ago was, you don't necessarily want these robots to run right up next to your obstacle and skim past. So you can go in once you identify an obstacle, and you can add an artificial value to the cells right around the obstacle to say, I'm going to penalize you for moving too close. So the cost of moving adjacent to an obstacle, I'm going to add 5 to, right? Or some number, right? I'm going to make the cost higher. That's going to encourage the robot to find its lower cost path a little bit out away from from the obstacle. And you can make that actually trail off instead of being, so right now it's a knife edge, right? The obstacle's here, it's hard, it's impossible, down to 1 for the cell next to it. You could curve that out and make it very costly next to it, a little less costly away, and make it the cost decay away. Okay. So that's how you can you can control the way way the robot moves through, interprets the cost of these things as part of what you build.
That could be useful if you're doing a three-dimensional object, and by weighting how close it's going to be, you could possibly avoid even having to be concerned about some portion that sticks out, because you said near that area it just costs more to get here.
Right.
We know that's going to occur, and so you don't have to. Your robot no longer has to think about that. It's intrinsic in the map, even if you did that on the dynamic.
Right. So the way you're controlling think of this as a surface, right? And so if you've got obstacles that you can't go into and then things you can, that's a very steep curve. But if you fillet those out and make it a little more costly, a little less costly, a little less costly, as you go away, you've got a lot of control over how the robot's going to interpret the environment. Okay.
Which is how we do things when we're, for example, driving down the highway. You're in a lane, and you don't think of it in terms of a cost function, but you really don't want to be like on the boundary of that lane. That's not a good idea.
Yeah, we think of it as, you think of it like mentally as little springs, right, that are pushing you from each side, keeping you in the middle of the lane, and you don't physically bump into something, but mentally you're like, I don't want to be over there at the high cost, right, the high danger. And you can make that cost function whatever you want. You can interpret it as, I find it risky to get next to sharp drop-offs. Or you could technically make it, this doesn't take into account speed. In some of the more other algorithms that are like this, that actually take the speed into account too. Directionality is another thing you want to add on to this, because this assumes a robot could make a 90-degree turn in a 1-foot space. Not all robots could do that. So you, in that case, as you're stepping from the start to the goal, the direction you come into the square is going to artificially add costs, make obstacles on sides you can't turn toward. And that'll force the robot to make, more sweeping turns if you've got a 4-wheel front steer robot.
That's why auto body is so expensive, to make sure you don't get too close to that big truck, right?
Yeah, right, yeah. And why self-driving cars,
Yeah.
self-driving cars are doing this, right? This is essentially what self-driving cars are doing
Same
continuously.
algorithm? You mean same
This algorithm, yeah,
Really?
or variation. Some of the more advanced versions of this, but this algorithm with some of the optimizations. It's all about the sensors. Right?
Well, you gotta be doing it like several times a second, right?
Oh, thousands of times a second.
Yeah.
Yep, because that way if something shows up within a millisecond, they have a new path, and they're redirecting the car to execute that new path within milliseconds. All right. There we go. Okay, so there's 3 main components here in the A-star algorithm that get calculated. And they're typically called the G cost, the H cost, and the F cost. And that's just from day one, that's what they were called. So the name is stuck. But the G cost is the distance from the start node to the current node, the sum of the start node to the current node. So in this case, the G cost from start to the green, which is our current node, is 3. Because it's 1, assuming it's 1 for every horizontal move and vertical move, and 1.4 for every diagonal move. Right, so the cost there, the G cost would be 3. The H cost is an estimated distance from the current node to the goal. Because you don't know the real node, you know what its minimum is. The minimum is going to be some straight line between it. Depending upon the computational time you're willing to spend, there are various distances you can calculate. You can calculate the Euclidean distance, just delta x squared plus delta y squared square root, right, of that distance. You can calculate that. Because you're doing squares and square roots, it can be computationally intensive, and your processor might not do floating point math well. So a very common approximation is called the Manhattan distance. They call it the Manhattan distance because it's like streets in Manhattan. They're grids. So in this case, the Manhattan distance would be how far it is in X and how far it is in Y, or how far horizontally and vertically. So in this example, the H cost in the Manhattan algorithm would be 1, 2, 3 to the right and 1, 2, 3, 4 up. So it would say the Manhattan distance is 7.
I'm not sure I do.
Okay, so think of the grid now as streets.
Yeah,
How many blocks would you have to walk to get from here to here? I'd have to walk 1, 2, 3 blocks this way, 4, 5, 6, 7 blocks
for the H cost.
for the H cost.
Yeah,
right?
okay.
Using the Manhattan distance heuristic.
Why wouldn't you compute for the H cost just going from start to goal straight?
Because that doesn't tell you, for your first node, that's what you would do,
Okay.
right? So when you're, the algorithm, right, we're
I
going to
see.
start at the start node,
Oh,
right?
you have an intermediate node, which is the green one.
Right, and so what we're going to do, and I'll show, we've got an example of this in a second, but you start the robot at the start node and you look at all of its neighbors.
Okay.
You calculate the G cost, which is going to be 1, 1, 1, 1, 1.4, 1.4, 1.4, and 1.4.
Okay.
And then you calculate the H cost, which is 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, is going to be there. And then you say, okay, my cost is going to be, the F cost is going to be, to go here, is going to be, well, 9, is going to be 1 for the G cost, so 1 point away from the start, and it's going to be 1, 2, 3, 4, 5, 6, 7, 8, 9 for the H cost. So the cost of that square is 10. If I pick this one, now the cost, distance from the start node to the current node is 1 still, but now the estimated cost of the H cost is 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. 11 plus 1 is 12. That's shaping up to be a worse place because that's 12 and that's 9. I probably want to go that way. Yeah.
Out of curiosity, what's the orange? Is that?
That's an obstacle.
So
Yeah.
okay.
Okay, and I can't go, so now I decide, okay, I'm going to move here next. So my path is going to put this on, and I recalculate my costs. Well, that's not going to be a neighbor. I'm going to calculate that cost for all my neighbors. Pick the lowest one or ones, because there could be ties. Whichever one's the lowest, I'm going to go ahead and start that as the next example and do the same thing with its neighbors. Keep building this map out, and when I find the lowest one, I put it on stack. Right? I keep track of my path through the lowest path until I get here.
I was trying to think of how I would do this, and you know, a two-dimensional array comes to mind.
Right?
And then after what you just said, I'm wondering if you'd have to do it as a heat map, like the obstacle would be perhaps a 255, so you can't go to 255.
That's a good way to do it. Or you just depends on how much programming you do, right? In object-oriented programming, you build a cell to have a lot of data in it, and you can say this is a closed cell. Because what we're going to look at the algorithm here, you run several stacks. So let's go through this real quick, and I'll point out where you're doing that. So this is the this is the pseudocode for the algorithm. You end up you create 2 stacks: the open stack and the closed stack. The open stack is a set of nodes that need to be evaluated. The closed stack are the set of nodes that you've already looked at. Remember we said this is a directed acyclic graph. Acyclic means it can't loop back on itself. You can't just get into this thing where you're going back and forth between two nodes. So when you look at a node, you put it in the closed stack. You put all of your obstacles in the closed stack, so you don't even look at those. Okay, and so you start this loop though, and you take your start node goes on the open stack to start with. That's the first move you make. You then take that node, since it's the only node in the open stack, you pull it off. Current is where you're starting from. And you add that to the closed stack, because I've already been there. Now, if the current node is the target node, you're done. Leave, right? You can leave. But if it's not, for each of the neighbors of that start node, each of the surrounding neighbors, if it's not been traversed, or its neighbor is closed, just skip it, right? So if it's closed. If I've been to it, it's an obstacle, board edge, whatever, just go to the next one. So now we get, if the new path to the neighbor is shortest, or the neighbor is not in open, so if it's a new node and it's not the shortest path, then I set that F cost. I say, here's your F cost of that node, and I set the parent of it in the path. This is really convoluted. We probably look at the pseudocode and figure out better than explaining it. But you set that parent so you can trace yourself back. You can get back to the path. And then if it's not open, you put it back in the open to be checked again. Yeah, whatever.
I missed the first part. Is this for dynamic mapping or is this static map?
Either one. It's just dynamic would just be you just do this over and over again, whatever it is.
So I mean, it would be updating based upon the data coming in, whereas a
Yeah.
static map would be just path plan.
Mhm.
And this is the course you're going to take, like in Google Maps, right?
Right. If it's a static map, you do it once and you follow the path. If it's dynamic, if obstacles can come in or people can cross your path, whenever your sensors find something new they put into the map, you rerun this and recalculate your path based on the new information in the map.
Or, yeah.
But notice that new
Outstanding.
path, you'd be adding close to it, and so you really don't make the speed through the routine much. It doesn't take much longer to run it for putting a new obstacle in.
Right, yeah, because you're skipping the obstacles
So
anyway.
you're skipping it.
Yeah, and this literally runs in a few milliseconds. This is like, it'll pop right back. And I'll show you in a second. It's even JavaScript code, so it's not even really fast code. Anyway, Lee, I won't go through this in painful detail because hopefully you're just going to go get a library, a Java library or a C++ library or something, and drop it in. It's more that you know how to set it up and build it. And if you want, there's lots of information on the web if you want to get into the specifics of how this stuff gets put onto the stacks and recreated. Okay, let's go over here now and run this. All right, so here's my grid. Built this big room up, and the green is my start node, and the red is going to be my ending node. So let's just take the example we had before, which is the robot starts there, and I want to do something in that chair. And I've got, oops. This mouse isn't right in real well. Let's do.
What are you using to generate this?
This is JavaScript. It's just a little program.
Okay.
How advanced is this? You made a maze, would it be able to,
Yeah, we'll make something more complicated, but it's just hard to draw this thing. All right, so let's say I blocked this in. This is the table. This is the obstacle, and I want to get from the green to the red. We're going to use the A-star algorithm, and we're going to use that Manhattan distance I described. That's the configuration over here. All right, and we're going to allow diagonal moves.
See if we'll read that better than the table.
No, that reads it worse. Oh, all right. Now this mouse is really touchy and stuff. All right, so we're going to do that. Found it pretty simple. All right, that took 5.6 milliseconds in JavaScript code on this computer to run, to build that out. Now, it obviously took longer to draw it because it figures it out, then it goes back and redraws the map.
Is it online? It looks like you're in a browser, right?
It's
Going
it's
to the server?
JavaScript, it's
Oh, it's
Node.js, so it's
JavaScript,
just
okay.
running, it's running in the browser.
And you're constraining this so that you can move in one of 8 directions?
One of 8 directions, any
Okay,
8 directions.
from each node, okay.
Right, now if I want to change this and I want to say don't allow the diagonals, I'll just uncheck that.
Okay.
Because it doesn't allow diagonal movement, it changes the, it has fewer options,
Mhm.
right?
So why did it bother checking down below, I guess? Is that what
Well,
that is?
because as it started to build out the weights of everything, when it got in, it started out here, and as it went this way and this way, that's really the same distance from there. So it really hadn't determined a winner yet.
Mhm.
But once it got over here, it realized, okay, this is probably, because if you draw the diagonal through there, right, it's going to be able to make that a little bit closer. It had to come here before it figured out that's a better path.
And the green spots, it's like, I don't care.
Those are the
This one
spots,
doesn't.
those are spots that it evaluated but did not put in a possible path. So like you said, there's no way those are going, if I'm going to come this way, it's got to be straight through. So let's do a more complicated diagram now. Let's say there's it's not going to be exactly a maze, but we can make it pretty close.
What does it do if it runs into it, you can't get there from here?
It
What if
stops.
you just ran all the way across top to bottom?
I'll do that next. Let's,
All right.
let's search that guy.
It's like water.
Is it going left to right? Like,
Hmm?
how, it looks like it's going left to right from top to bottom? Is that the way the program is?
It will generally move itself toward the, on paths
It's going
toward the
in like
goal.
utility, and I'm assuming it's going positive first before it's negative, or?
No, let's try it again. So I'm not sure what you're asking.
Turn the red to green.
It's going every
The
direction
location.
simultaneously.
Yeah, it's going, it starts at that start node, the green node, and it looks at the 8 nodes around it. And it says, oh, let me allow the diagonals too, because that's, letting it move diagonally makes it more efficient. But it looks at the 8 nodes around it and says, okay, which of these is the best one to go to? Well, probably all of them, because it really doesn't have a direction yet with the first couple of nodes around. So it kind of starts doing a Dijkstra algorithm effectively right around it, just a brute force search of the space. As that brute force search starts to expand, it finds areas that it knows are not better than what it's already found, right? If I keep going left, I know that's not the right
It's gonna reach a
direction, right?
threshold.
I don't know in the right which one's better, but I know going left is a dead end possibility. So I'll keep putting my efforts right. Well, there's lots of opportunities in this maze to go right. So it's going to try some and realize I've gone down this path, it's going to fail. So I'm going to stop and I'm going to go a different direction. Let the winners start to emerge.
Can you show them a Dijkstra run on that? So
Yeah.
you See the difference?
Yeah. So if we do the Dijkstra, which is this one, the Dijkstra is just going to literally, until it finds the goal, it's just going to search every possibility. The Dijkstra is very efficient in where there's not much open space.
Is it assuming it doesn't even know where the target is
Right.
either? Oh.
Well, no, it does know where the target is, because part of that calculation is how far am I right? How far is this node from the target approximately? That Manhattan distance or one of the other distances you can pick.
The difference is the dice star is a pure brute force,
Yeah,
and the A star adds heuristics. It's a little intelligent.
yeah, and that's when you look at the D Star and those other versions of these modules. That's what they're doing. Is they're finding various ways to trim off paths that are not going to lead to the solution earlier, so you don't have to search it.
Yeah, I get, and that's kind of why I was seeing that searching some areas that are fairly obvious to me that you wouldn't want to go that way,
Yeah.
but.
But because you can see the whole map, right?
Yeah,
And
but it's
it can
seeing
just see
outside.
itself and each surrounding and knows how far away it is. So it doesn't know these walls exist over here on the right until it encounters them.
Okay.
That, as brute force as that was, took my computer 49 milliseconds to actually calculate the solution.
So that was in real time then?
That wasn't real time. No, that's slowed down so you can visualize it.
That's what I thought.
The actual calculation, you can see in the lower left down there, it tells you it's 60.36 units and it's 49 milliseconds.
Can
But if you
throw
actually-
the other one back up, do the same thing and show them how much
Yeah,
faster?
do the A star.
Yeah.
But if you had to transverse, actually make your robot travel that, it would be insanely different, I guess.
Why?
At
At this point, it's just a path follow. You're just doing line following,
Okay.
right?
This is before the robot starts to move. This is the
Oh.
robot making the decision of which path it's going to drive.
So you gave it the map, and now this is, okay, I'm looking at it, and then I make my.
Those are the two options, right? I can, if I know the map and I know the map doesn't change, I'm going to just put the map in the
All
program.
right.
Right? I'm
And
gonna
that's
draw it
where I
in.
got confused. We're not exploring, we're
Well, you
looking
could
at the
be.
map and making a decision.
You could be. So let's say we did this.
What if exploring was, you're over here in the green here, we're on Mars, and over in red, there's where our lander is. I just need a path to get me there.
So-
Does it take into
I'm gonna look
consideration
at it
the
on
amount
the way.
of squares it has to travel?
Yeah.
Okay, because I was
Yeah.
wondering, because it looked like this path on the outside might have been quicker path based on the amount of squares that you went, but it's
Yeah.
hard to tell. You have to-
Well, we're looking at the cost, how much
Right.
it costs, how much it costs.
Yeah. And diagonal cost more because it's farther.
Okay.
So it says 1.4 for the diagonal cost versus
I see.
1 for horizontal. But let's do this. So let's say I drop this thing in the middle and I tell it I want you to go to the red dot.
Mhm.
So the first thing it's going to do is go, yeah, I can get there, bang.
Yeah.
Okay? But now we're dry for a little bit and we move the start location to there and we realize, oh, I found a wall. Okay, I can't continue on my path. Let me redo it. Okay, now I'm going to go that way. So I'm going to adjust. I'm going to stop, throw out my old path. Okay, I'm going to do that. So now we move along the path and we get to here and I end up with that. I maybe would have seen that. But, like, oh, okay, now I'm blocked again. We rerun it. Okay, I can get around there, right? And so you keep doing it every time you add something to the map, you just rerun the algorithm, and that's 1.2 milliseconds in
And notice
reference time.
when you put a weight of 1.4 in there, I mean, I don't know whether mathematically it would matter on this small sample, but 1.4 is very, very slightly less than the real number for the actual distance across there, which would be 1.41 something or another.
Yeah.
Anyway, the point is, so that would make this algorithm tend to pick diagonals whenever it can because it's
Right.
always more cost
It'd
effective.
be two versus 1.4.
Right, because
Right.
if I change this over and I make it be, don't let the diagonals happen, I rerun it again, different path.
Very good.
You know, I was just thinking when humans are faced with this kind of decision, they do a lot. I think they do a lot of like estimating, like that more complicated pattern you had.
Mhm.
You could just see that. Well, if you went up this way, it's about the same as if you went down this way and then up.
Mm-hmm.
And I'm just wondering if there's like, if there are algorithms that do that,
Yes.
take into account the cost, the computational cost involved. In other words, if you wanted to speed things up, if 5 milliseconds is prohibitive, then and you wanted to get it down to like a millisecond,
Yeah.
does anybody
That's what those other algorithms,
Okay.
the D star and some of those, there are ways to optimize even the A star. The thing that as you optimize, what you're doing is you're going though from general to specific. When you optimize an algorithm, you're saying, I can make this run faster in this more narrow, limited set of situations. Because I know it's mainly open, I can do this, right? Where that would be counterproductive in a very convoluted maze.
Can I talk for a second about
Yeah.
how Ross does it? So what they do in Ross usually is they have two of these maps. They have your global map, which is getting from your current start position to your end position, which is lower resolution because the detail doesn't matter. And then this algorithm can get a lot slower with higher resolution. So then you do a local cost map, which is your immediate obstacles that you're not trying to get to the end goal. You're just trying to follow the main path. And then since you deal with a smaller map, it just takes a section of that map. It can then calculate that faster to avoid, moving objects and things like that.
And if you get the resolution, I mean, that's one good way to do it, because we have this trade-off between bigger cells. I mean, you can do it
That's
quicker
true.
because you're going to go center to cell to center to cell. So
Yes.
if you're not 1 foot but you're 3 foot or 5 foot wide sections, you can jump through that. But then when you got to go through a door, that's not going to help you, right? Because the
Right.
door,
Yeah.
you need to be able to go. The square has to be in the middle of the door.
Right.
So you might need 3 squares to even fit yourself through the door.
But when you're comparing that to the way we think in estimation all the time, and computers think in facts. So when I'm looking over there and going, I wanna go to that building over there, I'm making an estimation of my past success at running across the highway and know that ain't gonna happen. So I've eliminated all that there, that a computer would have to go experience that today at this time in some method in order to put it on that map.
Yeah, although part of what you're talking about there is learning.
Right, well, that's what I'm saying, instead of using sensors, we use our memory as
Right.
sensory input.
Right. And that's one of the big things with AI, that humans have this trail of experience, life experience that goes way back, where the best AI computers don't have that. They can be very book smart about what they've learned, but they have very little experience to draw from. And that's until computers can get to the point where they actually have history, experience, it'll be hard for them to make really human-like decisions. That's why we don't let 5-year-olds vote, right? Because they don't have the life experience yet to be able to make those, or drive a car or whatever.
I
They
can
could
kinda-
physically do it.
I can kind of picture a warehouse robot being the most basic as far as what we're talking about right now. Should be a clean floor, nobody's walking the area if it's all robotic, and it's going to be strictly A to B, nothing ever moves. But if you took that same robot and poured oil or mud across the floor and then didn't change anything, it's going to make horrible mistakes.
Right.
Sure.
Or we
Yeah.
have to understand, I understand it can recognize that by a sensor. I can figure out this is a bad area, and I'm gonna make it an obstacle.
But think about like the FedEx, like storage, one of their big storage places, it's like, there's a reason why they have tracks and like, et cetera, for those things to go on.
Makes
So they can minimize all those choices.
Yeah,
Yeah,
it's
well,
always
even
going to be
though-
the same thing.
Even the little robot at Schnucks that goes around and does inventory, when you get close to it, it just stops.
I've never been there.
Yeah, it'll stop and it'll beep, but it's a turtle. It just pull up in its shell till you leave. Yeah, but it'll just pull up in its shell till you leave, and then it'll go on about its business, right? It
But
doesn't-
that eliminates some of those hazards, I guess.
Right.
Is
Right.
The response is no response at all.
Right,
I'm going
I'm
to
just gonna
stop.
But,
Wait.
that's why this is a
Oh,
complicated
they're
math
humans.
though, too, right? Because this path planning just plays one role in the overall architecture. Obstacle avoidance is a whole different thing. So part of your obstacle avoidance may be rerun the path planning, maybe stop. It may be shoot an electrical bolt at somebody, right? Or fire a weapon or something, right? Pick it up. Might be obstacle avoidance. So it might, and mapping and localization is the same thing. This is a separate task all to itself. It's not path planning. It feeds into path planning, and path planning feeds into it. But they aren't the same thing in architecture. This is where Ross, I think, really comes to help people, because each of these things, the implementation of each of these is a Ross node, and you're just publishing your results. So Obstacle avoidance says, I found an obstacle, I update the map, and I tell path planning, go recalculate. Right? And it goes and does whatever algorithm it needs to do to recalculate. Right? And the goals up here, like we said, they can change. I can be in explore mode until I find something through mapping and localization, and then I move over to self-improvement or to move and improve. I find the blocks. Now I pick them up, start to do something.
It's also, you know, when we're talking about path planning here, it looks like you're just doing the length of the path, but I mean, it could be something as simple as my steering system doesn't work very well, but my motor drive is great, so I'm better off with straight lines than I am any kind of turn, so minimize your turns. And then if you went back and you did that same thing, you would go back to what he did with the eliminate diagonals. But basically, it's going to try, I'm going to go straight and turn one time and then go straight up to it. That's what its best path would be.
Well,
Just
the
different
most
set of
part-
rules on what makes the cost of entering a new, I'm thinking of hex, because that would work on a hex map real well.
Yeah.
But,
And you can
on
extend
square.
it. You don't need to be squares necessarily. You can make them hexes. You can make them whatever's convenient.
I've seen people do different cost functions, like you can, if you can identify people, you can increase the cost of people and make it so your robot,
Right.
you know, doesn't brush or, it respects personal space.
Yeah.
Sure.
You know.
A lot of these algorithms you got to watch too. They work really great with if everything is a convex surface, but you put concave obstacles in there, and they'll drive in and get stuck. Different algorithms will behave different. So that's some of the optimization. They can be really fast, but if it's a concave obstacle, they're going to get stuck. So you force everything convex, and then you can use a faster algorithm.
Well, another thing about more turns you make, you always have to we all slow down for turns. They
Right.
probably do too.
And this is an algorithm that doesn't really take that into account directly. There's actually some better algorithms that do that, but they're very complex.
You need bigger
matrices.
computers.
You need bigger computers, right? And you need a lot more math to. You basically have to model the robot as a mathematical function that includes speed versus turning ability, like a drone, right? It can only climb so fast, it can dive so fast, but the faster it's moving linearly, the longer it takes to do a turn, right? Because it's going to squish out. So you have to constrain the path planning to take into account the speed, right? Does it slow down to make that tight turn, or does it stay faster and go out a little farther
Oversteer.
and oversteer? Yeah, and that's so you can get. There's a lot of different variations of this. So this for what we do. This is a very good starting algorithm to do that with. But
I was thinking the next level for line following would be where you'd have to run the course once, but essentially learn it to this level, and then have to the ramps 3D printers supposedly they have look ahead, so they know where this point's gonna be, so they'll go ahead and accelerate but decel,
yeah,
and then sort of as quick as efficient.
You mean behave as a race car driver?
Yeah.
Yeah.
And because line following, I think the sensors, it's always reactionary.
Right, it's
Which is
very,
worse.
yeah.
You need to be anticipate and
yeah. But at this point, besides some of those more complicated things, if you think of this as very one-dimensional. At this point, you're doing line following, right? My sensor, my direction isn't my sensor, my light sensor's on the line. It's just my error function is still, what is my telemetry telling me I'm deviating from that line, from those
shortest
XY
path.
positions.
Yeah.
Right, so now what you've got is, that line, what you got in the program is a linked list of XY coordinates of cell centers. Right, so you have the XY coordinate of, the XY coordinate of that center, the XY coordinate of that center, of that center, of that center, right? So that's what your data structure comes back as. You then give that to the guidance program and say, follow these, drive from this waypoint to this one, which is every foot or every 1.4 feet. And you tell it to drive that, and your error function is how far are you from that XY coordinate, or XYZ coordinate in the case if you're doing 3-dimensional.
You could do what Josh was talking about. You could come here and go, now I'm on my green starting square there, and I'm just gonna go to that next square that's got a yellow line in it. I can now create a new smaller map right there.
Right.
For that move, and make sure that I'm taking the best course to that particular location, which hopefully would be a straight line, but it could be something crazy in there for
Yeah.
some other reason.
Yeah. Okay. There's other ones we can talk about if you're interested. One of my besides this, I use for drones or things that don't have bounds or have memory constraints, is one that doesn't rely on the grid. It doesn't guarantee an optimal path, but it will find a path. We can talk about it at some other lecture, some other day if you want. But
I'd still like to know why the human brain is so good at doing these things, and like you were talking about before, we could have more and more complex algorithms, but it take more computational power. And already, I think we're up to like 100-watt CPUs. And if you think about a 100-watt incandescent bulb inside our head,
that's about what we have. I think it's 40 watts.
yeah.
40 watts.
So how are we able to get by with a 40-watt?
We also operate at the speed of sound instead of the speed of light.
Yeah.
But think about what we can do at the speed, because our brain functions at the speed of sound. Anyway, the point being, but a computer always has to make that yes/no choice, and we can go maybe, and that's what does it.
Well, and we operate in parallel. We operate massively parallel,
Yeah.
which is what wins
Yeah.
it for us.
That's right, and I'm just wondering what it is we as humans need to do to make computers more efficient in terms of their.
These biologically inspired algorithms
Mhm.
address that. There are ways to look at the map holistically, and they're still binary algorithms in the end, but they tend to try to model how humans think in parallel. One of them's called neural nets. Is not neural nets? Sorry. Genetic algorithms is one of them that's pretty popular. It's and the benefit of a genetic algorithm is you can let it run. The longer you let it run, the better solution you get. But if you're time constrained and you stop it early, you know you've got a pretty good solution. It may not be optimal, but you can stop a genetic algorithm prematurely and have a good solution. And it really, it's just like genes. It takes your state, all your various permutations of paths through the system, and it just starts comparing them. Well, what if I do this and this and this and this, and it builds a model. If that's a better genetic match than what you started with, it keeps that as the new offspring. And then it'll take that and mate it with another option and see if that offspring is better. And if it is, it keeps it, right? And it can do that very fast and in very parallel, because you can run separate threads, each doing those genetic matches.
One kind of answer, sort of, that I just thought of is we're okay with imperfection. Like,
Yes.
you know, if I'm faced with traffic, I could say, well, I go that way, that way, that way. Both of them look like to work. I'm going this way. Yeah. And not worry about.
Well, that's what
That's
Waze
part of
does.
it,
Right,
yeah.
that's what Waze is doing. If you Waze is taking real-time information about that you're giving it from having your cell phone with GPS, and it knows what road you're on and how fast you're traveling, and it knows how fast that road should travel. And it'll tell you, oh, there's an accident reported here, or traffic's backed up. I'll run the A-star algorithm from intersection to intersection, with the weight being the time it takes to get there and some factor for stoplights and stop signs. And figure out whether it's going to be better for you to wait in traffic until we think that's going to clear, or shoot around it through some side street.
But think about what we do in that same situation. You get like, theoretically, when the state or the city or whatever tells you the best path to get to the airport today from your house or any program, it's doing that and saying, this is the traffic speed, this is what we see at traffic on those roads right now. As compared to you making a decision tomorrow because the battery's dead in your phone and you gotta get to the airport, what are you gonna do? Instead of that thought process that the computer just went through, you have a completely different style of thought process.
Which is different whether you're going to Lambert or you're going to an airport you're not familiar with. You go to Lambert, you know the traffic patterns.
Right, and
You know you have a past history to base things on.
Exactly.
Yeah.
Yeah.
So
and
you don't need sensors for that.
also,
because we have it.
I was sort of saying, that computers have a long way to go, but actually, because computers are good at making decisions and not so good at sort of, you know, this fuzzy type stuff. What happens is they're excellent at doing mathematical computations. A computer can do a big multiply in a matter of microseconds, whereas any one of us would require, well, first of all, since we're so visual, we would require pencil and paper, or at
That
least
depends.
we
Some
have to.
people are pretty good. You could talk to statisticians.
But
They
when
can
I
give you
want-
numbers almost instantly.
What's
Well, I
that?
think what we're talking about too is like when it comes to decision making, when it comes to task planning, you have to understand data is only as good as it is for that particular moment in time. The problem is, like you're saying, with algorithms trying to optimize things. What's actually happening, in my opinion, is that you're actually training humans to make decisions faster based off of information that they can rely upon. And that way you're training them. It's like training mice. Like, okay, everybody go this way. Come on, everybody. That's what's happening. That's why things are getting better as far as like traffic is concerned. The problem being, though, that when you have erroneous things or just maybe data that's not accurate or delayed, that can be a problem. Also, you can't take in consideration what's going to happen 2 seconds from now. Okay, we can make an evaluation based off of previous data, but that doesn't mean that that's actual fact. You can come up with a concept that you feel is confident, but again, an accident can happen right in front of you, and you say, "Wow, I could never imagine that,"
Right.
and that could change everything.
Right.
That's why, in my opinion, like all these algorithms are good enough because
Mhm.
they'll never be perfect. There's no such thing as perfect. So
Also-
there's
yeah.
I mean, it has to fit a certain constraint.
Right.
What is your target? What is your model? Like how efficient does this thing have to be within a certain parameter? Like cars travel only a certain speed, so that's a limiting factor. So you take that into in consideration. That okay, what is half a nanosecond in this car that travels 60 miles an hour? It's nothing. It's kind of
And
pointless.
another interesting thing about that is when a human being faces a totally new experience. This is not a particular point, but you're a new soldier going to a war, and the first time a guy next to you falls over dead or explodes or something, the normal human situation there is you're going to freeze and try to process information.
Sure.
So the military does all of that training to try to get you where that freeze is as short as possible, and you
Yes.
can go on. Well, that's exactly when our system failed. That person that lived through that person's system failed right there. He doesn't have any background information here, so he cannot make a real choice. So now he's just processing on no information. What is he going to do? And you can see right there what a computer can do that we can't do, and what.
Yeah, and I think another thing is that what Craig was talking about before, which is that we have so many sensors. The human body has so many sensors, and so many excellent sensors. I mean, the visual is so good, and then we have a processor that was based around making those visual comparisons so efficiently.
I've heard different numbers, but somewhere between 40 and 60% of our brain effort goes into our processing our visual input.
You have a lot of problems too with humans versus computers. Computers know the constraint. Okay, so they know the threshold. Where human beings, we kind of have this idea of what's like how far we can see, but we don't know. We were not given a specific. I mean, I can look over here, and I don't know that's like 10.7 meters. But, I don't know that, but a computer will have that information.
Sure.
Period.
Yeah.
So it can make that decision. It's not going to worry. Whereas human being, you might weigh that into consideration. In the future, that might change, but I think for the moment, for the task that we have, automation running at, I think it's completely optimal.
I didn't put it on this diagram. Maybe it really should be. Is our ability to build a model of the world is very good, and what we're doing all the time is we have this model of the world in our head that we're adding to and taking away from. And it's not just a physical thing, right? It's concepts and ideas and
That's what a baby,
expectations.
Yeah,
right?
you can see a baby doing that, and it does all these weird things like holding things and sucking on things and all this kind of stuff. Well, it's getting information there, even though it's very rudimentary.
Yeah.
But the reason I brought that up is partly because I just wonder if this won't affect, at some point, I think somebody's gonna come up with an architecture for a machine that is not this binary-based thing like we
Yeah.
always use for everything that we.
I got a concept, it's just that we don't have the technology, but if you think of every location in a memory as being a quantum location,
Yeah.
where you can send an electric current through there and certain of the electrons in that particular location leave. You can now analyze the current in that location, and you can give choices that are variable.
Yeah, and I think
We're on
that's-
the edge of being able to do this.
Yeah, I think that's
But
kind
the
of how
problem is,
brain-
it's no longer a binary computer,
Right.
so I no longer want it to press the red button, because it could go, hey, maybe this is a good idea.
Yeah, and it's the neural nets, they're a thing, not neural nets, I keep saying neural nets, I mean, fuzzy algorithms,
Yeah.
right? They try to model it, they're not as,
Yeah.
not as successful as a human brain,
Mhm.
but that degree of membership, right? When does something go from cold to warm to hot?
Yeah.
Well, it's all kind of a continuum, right? And digital computers like to say, well, if it's over 375 degrees, it's hot. But if it's between 374 and this, it's warm, whatever, right?
Yeah.
And you, where fuzzy logic says, well, it can be warm and hot at the same time. Or it can be cold and warm, right? It's a degree of membership into the buckets. It's not a binary thing. And it helps. You can model things better with that, but it does not come to the degree of pliability humans have.
The one thing everybody forgot was, how did that obstacle make you feel?
Yeah.
Yeah.
Well, the first time I hit it.
Robots, you don't need emotions. It's
Yeah.
That's what I'm saying.
that-
We have a lot of wasted cycles, so to speak, on
Yeah.
emotion. I mean,
Well, that's where our
You get that.
experience can work against us, not for us sometimes, so.
Now, a piece you left out, I think, I'm
Mhm.
not sure, is how does this work, how does this mapping system, or whatever you call it, work in a situation where you can't see the target and you don't have the map built in? You know, where, in reality, we don't want to put the map in ahead of time.
Right, it's a lot of work.
We want it
It would
to
just
see
be-
and
yeah.
explore.
You have to have your
You'd have a
sensors.
threshold, you like say, okay, what's my viewing distance, and that would be a threshold. So that would be, of the
You can,
sensors.
you
but-
can drive around and bump into stuff. You have to have
Well,
some
it's like
sensors.
the first explorers, they didn't know the New World was here,
Right.
they just thought they'd go to China and.
But
So
they
you
drove
have
here and they
to-
looked around, right?
But guess
If
what?
you
They
can't look
knew
around.
they were looking for China.
No,
They had a goal, they were going to China.
Right.
So, in the fact that in the meantime, they found something just as good or better was lucky for them. But when you're talking about, you could still know you could still know this is here, you don't have any idea what's in the middle.
It's in the middle.
And then
I
your
see.
sensors on your robot they just created this teeny little L-shaped obstacle here.
Yeah,
Then it runs that program again, right there where
But
you are.
that's where you have to have some kind of sensor, a bump sensor, a
You have to have a
whisker,
sensor.
a
that
vision,
can be
whatever.
But you can't really determine your path ahead of time, you have to explore.
No, so, right, and
Yeah, well,
that's, explore would be, I'm gonna go from England to China,
Yeah.
right? And as you sailed across, you ran into this obstacle.
Mhm.
So at the point where and now your maps change. So now you go back and say, do I still have the same goal? Maybe not. Maybe now I change my goal to something else.
Oh.
Or I still want to explore, but I'm going to explore here. So I look around and build a map of what I see. Just like one of my
It's just
favorite
like-
games was
and that's-
Civilization.
Cabot.
Right, when you start with no map and you just move and it
Well,
expands the
so-
vision
Bizarre
around you.
with south.
Well, the point is though, it's gonna be a lot more.
It's a lot more
random.
complicated.
Trial
It's gonna
and
be a
error.
lot more updating, yeah, and
Yeah.
random, just kind of searching out.
Right.
Well,
And
look
that-
at the way Lewis and Clark had to cross the the United
Yeah,
States.
right.
Well, I mean,
They're
if it's
the
random,
source
it's
of
not
data
about
and
path-
what was
I mean,
Indian
If it's a random
preference.
thing that you're doing, it's
Yeah,
not
but-
necessarily, you're not pathfinding. At that point, you're mapping. If it's random,
Yeah.
otherwise you say, okay, well then, if I'm gonna what's the most optimum way to search in a pattern? That would be just going around and around in a circular formation, just continuously.
Craig, can
That'd
you
be
throw that,
something else.
can you throw that,
Yes.
the running, anyway, that, and put your start and your end on there, and just put a blank map there, or whatever, you've done this, but do a blank map,
Yeah.
and then have it come along and put one little obstacle in there and show them what it does, that you have to run it over each.